Hello and welcome. I am Géza Mark from Budapest, and the title of this talk is Ab-initio wave packet dynamical simulation of defects in two-dimensional materials. The outline, the wave packet dynamical method, how to prepare an initial state, block function wave packet construction, block function wave packet scattering on an object, and the band structure in kinetic energy operator, and the describing the infinite two-dimensional crystal with kinetic energy and local defects by potential energy. The general principles of the wave packet dynamical method is as follows. We have an investigated system which is described by the potential VR, and we have an initial wave packet, and this is the method calculates the time-dependent Schrödinger equation, and it calculates the scattered wave packet, and the scattered wave packet is symbolized by these arrows. It is scattered in different directions with different amplitudes. These are the input quantities, the VR potential and the psi0 initial wave packet. And the method calculates the time-dependent wave function, and from this we can calculate all kinds of observables, for example the probability density, the probability current, and the eigenstates. This is a simple example in two dimensions, scattering on a hardcore potential. So we have an initial wave packet, and this is scattered. The time is going like this. It is scattered in a spherical function which is in two-dimensional circle. And this is the real part of the wave packet. This is already a real calculation, a three-dimensional calculation. We have a tip of a scanning tunneling microscope, and we have a graphene surface. And the graphene surface is described by a carbon pseudopotential. This is the cross section, this is the STM tip, and these are the carbon atoms. And then the carbon pseudopotential is like this, that the atomic size, it has a large negative value. At the center of hexagon, it has a large positive value, and between the atoms, it has a small barrier. This is our system, and we have two cross sections. This is the first cross section XZ and the second cross section XY, and this is the time development of the probability density. This is the time development of the probability density. So the wave packet tunnels from the STM tip in the graphene surface, and it is spread in a complicated fashion. So that the initial state, which is on the graphene surface, is already produced through a complicated process. We utilized it in interesting calculations, for example, for graphene grain boundaries. This is this calculation. But the question is, how can we create precisely controlled initial wave packets on the graphene surface? So, or on any nanosystem. So we can build them from Bloch waves, because if the potential is periodic, then the Bloch theorem states that it is the wave function is the multiplication of two terms, a periodic part and a plane wave part. This is the Bloch function. It is shown in this cartoon. This cartoon shows the different terms. This is the plane wave part, this is the periodic part, and this is the multiplication of the two. And the color scale is like that we show the real part of the wave function. The positive is green and the negative is red. So this is the graphene Brillouin zone. First we are in the middle at the gamma point, so of course the plane wave part is constant. Then we are halfway between the gamma and K, so we have this plane wave, and then we are already at the K point. We have this plane wave with decreased wavelengths, and here we are at the extended Brillouin zone, 1.5 gamma K. And it is interesting that this U part, the periodic part of the Bloch function, its symmetry is changing. It doesn't remain hexagonal. And these are the Bloch functions. And the next step is the construction of wave packets from Bloch functions. We can do it through an integral in K-space, in reciprocal space. So we have the Bloch function, and we integrate it with a kernel, this AK kernel, which in this example is also a Gaussian multiplied by a plane wave, which is shown in this cartoon. The kernel is only changing in y direction, so it is our kernel, Gaussian multiplied by a plane wave. And this is the result is a Bloch wave packet, which is shown in this cartoon, a Bloch wave packet. And then the next step is that we calculate the time development of the Bloch wave packet. We have 3 different examples. In this example, we have a pristine graphene surface. This is the initial state, this is 3.6 femtosecondum, and this is 7.2 femtosecondum. We can see that the wave packet is spreading in the y direction, and its shape doesn't change. This is because we are near the K point, and this means that the dispersion relation of graphite at the K point is nearly linear. And in the second row, we have already a structural defect in the middle. We have a structural defect, and then the wave packet is scattered. And this shows the scattering pattern. This is simply the difference of the 2 wave functions, and this is the absolute value. And we see that it has a hexagonal pattern, this scattering. This is the time development of a Bloch function on pristine graphene surface, and this shows together on the left the perfect graphene and the defect, and this is the difference in the right, difference of the 2. It shows a hexagonal scattering. This is the scattering itself. It shows the hexagonal scattering, and this is a zoom in. We can see. The next question is that how can we make wave packet dynamics for other materials? In the split operator method, the kinetic energy is calculated in K-space. The kinetic energy is calculated in K-space, and this is nothing else but the free space dispersion relation, this K square over 2. And the question is, what happens if we modify this? Actually, we can modify and calculate it from the band structure. We show 2 examples. The first is a test case, graphene tight-binding dispersion relation, which is along this analytical formula. And this shows the initial state, this is a Gaussian at the K point of graphite. And this is the time development, the wave function, time development of the wave function, the probability density, and this is time, here and here. And we can see that it spreads along a triangular pattern. The wave packet is split into 3 parts as it travels on the graphene surface. This is because of the anisotropic nature of the graphene dispersion relation. And if we put it in the other K point, opposite, at the K prime point, it also spreads in this triangular symmetry, but rotated in 60 degrees. Yeah? And here we have both K points, the K point and K prime point. So this cartoon shows that if we have two Gaussians, then the Fourier transform is a Gaussian multiplied by a modulation. So really, we can see that it spreads along a hexagonal pattern and it is multiplied by a plane wave. And if we have three Gaussians at the three K points, then the modulation then the modulation is along a triangular pattern. If we go back, why we have seen here a hexagonal pattern? Because one of the points was a K point and the other was a K prime point. Okay, so this shows the three K points case, the spreading. It is interesting that in the spreading we have this atomical scale pattern, though in this calculation we have no atomic structure. The atomic structure is actually present only in the dispersion relation. So when the situation is here, that the initial state is that all the three K points and all the three K points are occupied, and then the spreading is like this. It is a hexagonal spreading multiplied by an atomical scale pattern. And this shows all studied cases. For the 1K point, the K prime point, 3K points, and all the 6K and K prime points. And the next calculation is for a more complicated case when we have a molybdenum disulfide dispersion relation. We only show it briefly, it was published, and this is a complicated spreading of the wave packet. And what happens if we insert a structural defect in the material? This can be done by the following trick, that the infinite crystal is modeled in K-space and the local potential is modeled in direct space. So here we have a pristine graphene surface described by the kinetic energy operator, and then we see that the spreading is hexagonal. And in the next part we already have a potential, a Gaussian, and we can see that it produces a scattering. This is the difference of the two. So the scattering is along a hexagonal pattern. It is interesting because the potential is isotropic, but the spreading is anisotropic. We can say that it is a modified Huygens principle. We have a scattering, but it is not a spherical scattering, but it is governed by the dispersion relation, which is anisotropic. So how can we go further? We can calculate wave packet dynamics for more two-dimensional materials, and we can utilize the multi-domain method. So in different spatial regions we can use different dispersion relations. So thank you for the attention.